The purpose of this script is to demonstrate an analytical solution to the least squares linear regression problem. First, we'll derive a set of equations and then test them on some model data, introduce some statistical concepts such as bias, and then finally test our solution on some real-world data. Least squares linear regression seeks to fit a linear equation to a set of dependent variables that can predict some independent variables. The goal of this being to minimize the sum of squares of the residuals or the differences between the predicted independent variables and the actual independent variables. We will treat these dependent and independent variables, x's and y's respectively, as vectors of observations and then combine them into matrices. We will then seek to find a matrix of betas or coefficients that when applied to the x's will give us an optimal solution for predicting the y's. So this illustrates that our goal becomes to minimize the expression, the absolute value of y minus x beta squared. We can rewrite this same solution in a different form, as you can see in this extended form here. And further, we can rewrite this as a function of beta in this other form. And the benefit of this is that this contains the Gramian matrix, which we know is positive definite, which helps us because we can then set the initial term to 0, and this will minimize our equation. So first, we will generate some data to spot check our solution and see if the minimization works. And additionally, afterwards, we will introduce error terms. We will make these error terms have a mean of 0, and they will be normally distributed. And introducing these error terms echoes real-world applications because that often contains noisy data, and we can thus demonstrate that such a solution can be used to solve real-world problems and gain some predictive power over these sort of questions.
All right. So just to go over how exactly we're going to implement this in R, we'll start with generating some data. So we're going to decide we're going to use 200 observations as our sample size. And then we'll generate x's as 200 observations of a random normal variable with a mean 1 and a standard deviation of 2. And then we're going to generate those error terms that we're using to model, I guess, noise in our data with this vector of 200, mean 0, standard deviation of 2 observations. So then what we'll do is we'll generate our y. And it's important to note here that the relationship between x and y is that y should be 2 times x plus our noise function. So if we're looking for a relationship between x and y, we should be looking for that too in an ideal coefficient. Then we're going to also generate our x matrix, which we'll do by taking our x variable and adding on a vector of 1s, which will be used to model a constant term. So if we're thinking of trying to model the equation as y equals beta x plus some constant, adding on this vector of 1s will insert the constant or the y-intercepts, it'll be the average of y. So what we'll do then is we'll put in a function which will solve the normal equations that we described above, and then we'll display it. So let's do that now. So here we got our estimate for beta to be 1.959, which is pretty close to 2, so that's roughly what we're looking for, and then the constant being 1, which again, pretty close to what we're looking for, so that's good. So now what we want to do is we want to say, given the data that we've generated of y and x, are we actually finding the minimum solution to this problem? So the way we thought to do this is not analytical, but we can numerically just run through a bunch of calculations of the sum of squares, which is what we sought to minimize, and that's in this equation. And that lines up to this guy up here. And we'll create a matrix with 100 entries, and for each along one of the axes we'll mess with the bottom variable, and one of the axes will mess with the top variable, so we'll create 10 possible different values for each of them, and that'll, in combination, create 100 possible different values of the two. So then we'll do that in a nested loop here, and then we'll display the matrix. So see what that looks like. So you can see the matrix is fairly, it seems that the numbers are getting bigger around the edges, which is what we're looking for. So here we see this appears to be the minimum value, but let's check. And we can see, there we go, just so it's in the window. So there we see the minimum is that value, and it's at row and column 5, which you can see this corresponds to when I and j equals 5, so these are just the estimates that we estimated unperturbed. So it looks like we have actually minimized the sum of square errors, which is what we sought to do. So our second question is whether our assumption for noise is actually giving us an estimator that models the true relationship. Like, we got pretty close to 2 in our trial, and we know 2 is sort of the value we're shooting for. If we do this a lot, did we just get lucky this time, or are we going to tend to find a beta close to 2? So what we decided to do was generate 1,000 different sets of data based on our formula above. So we're just going to do that 1,000 times in this loop, and we're going to fill in a matrix of all these different betas that we estimate based on all our generated data, and then we're going to show what that what that matrix looks like. So let's run that, and then we're going to generate the mean, and we're going to generate a histogram as well. So here we can see the histogram. It looks like the center of it is pretty close to 2, which is good, and it also looks fairly normally distributed. So this isn't exactly the way one would go about statistically calculating what a beta should be, and once again the mean is very close to 2. Because in the real world you can't just generate as much data as you want. You only have the data set given you. But this does at least show us that our method of calculating beta, given our assumptions, seems to, in general, produce an estimator for beta that is close to the true estimator. And if it's far away from that, it's pretty unlikely for that to occur. So in the real world, what you'd like to do is you'd like to be able to say, okay, if we're getting a certain beta, what is the likelihood that that's far away from 0, or whatever your null hypothesis is. That's outside the scope of the script, but it would be, I guess, the next step for what you would want to do once you generated your estimator. So next, what we're going to do is we're going to try this on some raw data that we don't know the actual relationship, and see if when we calculate it using our normal equations, does the relationship we calculate that minimizes the sum of squared errors, is that something that makes sense? So the data we're going to be using is a diet that I went on once, and I calculated the number of calories I ate in a given day, and how much weight I gained or lost as a result the next day. So let's import that data. That's down here, and then we're going to put it in a matrix form so we can use our normal equations. So I do that now. Then we're going to check the length of the vector so we can add a column of 1s. I already knew it was going to be 89, so I put that in now. And now we'll just use the normal formula that we already have and display it. So you can see that the coefficient for the pounds I gain or lose per calorie is 0.00357. So it's positive, which is good. That's the relationship we're looking for. So the more I ate, the more I gained, and the less I ate, the more I lost. But according to this, that would imply that I'd only have to give up about 300 calories for me to lose a pound, which is pretty ridiculous given nutritional science. So clearly there are some other variables at play that aren't calculated in our data, by our equation. But I guess that's the nature of statistics. So thank you.